Hello guys, this is Professor AutoCAD here. Welcome back. So last time we mentioned that back in the year 1900, Planck guessed the general formula for black body radiation. Then Planck immediately realized that since this formula is correct, there must be some kind of truth hidden inside it, waiting for me to discover. Then Planck started to dig deep into the formula. So I'm not going to spill out the whole process to you guys, but mainly it's just multiplying a constant to the numerator and denominator called the Boltzmann constant. But at the end, Planck deduced a conclusion. Yet here we must list out a formula. But it's a very easy formula. You understand as long as you paid 0.1 attention in like year 8 maths class. E nu equals to nkc2 nu, where n can only be positive integers, and k is the Boltzmann constant, c2 is the Wien coefficient, and nu is the frequency of the electromagnetic wave. So it's literally a quadratic equation, a straight line on coordinates. But don't forget, n can only be positive integers, meaning the energy value of blackbody radiation can only be an integer multiple of a certain minimum value, and the minimum value is kc2 nu. Planck was like, k and c2 are constants, so let me times k and c2 together, and I'll represent it with an h, which became the Planck constant. Therefore, the formula now is E nu equals to nh nu. Same, n can only be positive integers. But on the other hand, this is not the case. This is not what classical physics would expect. We've never heard that there's a minimum value of energy and it is discontinuous. For example, there's an object. I divide it into half, and then divide the two halves into another two halves, and repeat it infinitely. It should be endless, but now it seems like after a certain value, I can no longer divide it. This is again confusing the classical physics, and Planck believed that he has discovered a great secret. So, on 14th December 1900, Planck published his deduction process and result, and he said, if the black body radiation formula is correct, then there must have an assumption. What is the assumption? It seems that the energy is not continuous. The energy of matter is like following one after one, an indivisible energy that spreads outwards in any form. So Planck calls this energy as quantus, meaning a certain amount of matter, which eventually became the word quantum. And this is the origin of quantum. Great! Planck opened the door to the original version of quantum theory and quantum mechanics, but it's still very different and unacceptable to classical physics. And as we said before, in 1900, Planck was 42 years old. At this age, being a prudent person, Planck had some concerns. So at the last page of his publication, he wrote something like this. I'm just saying, don't be serious. So physicists didn't really pay much attention to Planck. For example, Jean remodified Rayleigh's formula in 1905. It's already 5 years after Planck's publication, and someone is still trying to explain the black body radiation using classical physics. But also in 1905, someone did pay attention to Planck. Who was that? He's very famous. Albert Einstein. So, some of you might know about Albert Einstein. May say, dude, I thought Einstein published special relativity in 1905. Well, yes, indeed. That's why he's a bloody genius, publishing the special relativity and understanding the black body radiation at the same time. 1905, Einstein was, let me see, 26. He's young. And young people are more receptive to novel ideas. When we talk about this later, many of the physicists are basically made great achievements in quantum mechanics when they were very young. Einstein has heard of the photoelectrical effect. A beam of electromagnetic wave hitting the metal plate can eject electrons. It has nothing to do with light intensity, only related to its frequency. And now Planck's saying energy is not continuous. It's followed one by one. Each one of the energy is related to the frequency. Einstein was literally thinking, dude, you literally give me something to elaborate. So Einstein assumed energy is not continuous. An electromagnetic wave is energy. Light is a type of electromagnetic wave. So, therefore, light is not continuous. And let me divide light into one by one, and I'll call each one of the light as light quantum. Then an American physicist called light quantum into photon. Einstein said that a photon can also not be divided. It's the smallest unit, where the energy value would follow Planck's E nu equals to hv, where n equals to 1. Where h is the Planck constant, as I've mentioned, nu is the frequency of the electromagnetic wave. I forgot to tell you that the Planck constant is actually very small. It's around 6.626 times 10 to the negative 34 joules second. So if you see the Planck constant in any formula, then it's definitely a quantum-related thing. Then Einstein published a paper saying if you want to eject the electrons out from a metal plate, it requires a minimum energy value, calling it the work function, meaning an electron must receive at least this amount of energy, then it can escape from the metal plate. And now the photons come here one by one. As long as the energy of each photon is larger than the work function, then electrons can escape. So we can now have a conclusion. The frequency of the light must be larger than a certain value, then electrons can escape. And it just happens that the value of the frequency falls within purple light. That's why only frequencies on or above purple colored light and ultraviolet light can allow electrons to escape. Let's take the lifting stuff example again. So there's a heavy object. If one person can't lift it up, you need two persons. If you can't still lift it up, just find three persons. Just find three people. As long as you have a lot of people, you can eventually lift up the heavy object. But to classical physics, photoelectrical effect has the setting of this. The setting is that now is as long as the person who lifts the object is over 35 years old. I don't care how many people there are. It has nothing to do with your strength. It has nothing to do with how many people are there. You can lift it up by yourself as long as you are over 35 years old. But now Einstein's saying you can't understand the whole thing like this. These people are now ideal. And now there's a new property, which is their strength is proportional to their age. Which the older they are, the stronger they are. Meaning their actual age represents their strength. Whereas these people can't lift the object together. They can only queue up a line and do it one by one. One came, couldn't lift it, okay, bye-bye. Next, so now it seems like the scenario is related to age, but still it's still related to the strength, which for photons it would be energy. Therefore, in 1921, Einstein received the Nobel Prize in Physics in explaining the photoelectrical effect, but not for relativity because there was no experiment at that time proving that relativity was right. Great, we now had a good answer for photoelectrical effect and the blackbody radiation. But let me add something. Throughout the whole history in physics, no one really know what light is exactly. The arguments between wave and particle has never stopped. The person who first proposed the theory of the system is called Huygens. Yes, it's a weird pronunciation. He said that light is a kind of wave, just like water waves. Then he also proposed and introduced the laws of refraction and reflection of light, but could not explain diffraction of light. A few years later, Newton said that light cannot be a wave. It should be a particle. Someone said that the reason why Newton supported the particle theory was because of Hooke. Newton did not have a good relationship with Hooke, so Newton supported the particle theory right after Hooke supported the wave theory. Well, according to Newton, light is a very abstruse particle. But what kind of particle is it? What properties are there? Newton could not explain them. Why the hell are you doing that? God damn it. Since Newton was too famous, therefore for the next 1 or 2 centuries, people believed in the particle theory that Newton believed by instinct. Until the early 19th century, the wave theory seems to revive. From the diffraction of light to Thomas Young presenting the famous double-slit experiment, to Fresnel perfecting Huygens' wave theory, and until Maxwell predicted that light is an electromagnetic wave, giving victory to the wave theory. But suddenly, Einstein popped out of nowhere, giving the explanation for photoelectrical effect, suggesting photons. Seems like he's saying that light is a particle. Actually, at first, when Einstein suggested photons, not many people really approved him, because Einstein received the Nobel Prize in 1921, literally 16 years after his publication. It took 16 years for people to believe in him. For example, the American physicist Millikan. He didn't believe in photons in the beginning and wanted to prove that Einstein and Planck were wrong using an experiment. Came out, his experiment proved that they were actually right. So Millikan received a Nobel Prize in 1923. Really funny, isn't it? Okay, then people had to believe that light is a particle and a wave at the same time. The wave-particle duality. But when we talk about matter waves and the uncertainty principle later on, you'll find out that wave-particle duality isn't really that simple. Okay, let's rewind for a bit. Do you still remember the Balmer's formula? Balmer's formula. The condition is also that n can only be positive integers. Could this have something to do with Planck's quantum hypothesis of energy? And the fourth unsolved mystery, the stability of atoms. What is that? Well, that would be something for next time. Great, that's all for today. If you like my channel, please accent the like button, follow my Instagram account, subscribe and turn on the notification bell. And I'll see you beaver face next time. Bye!